Hello, everyone. So, our team is about surgical visual understanding, which is a deep learning approach to surgical tool recognition in robotic assisted procedures. Robotic assisted surgery has revolutionized operating rooms by enhancing precision and also reproducibility. The Da Vinci robotic system, used in over 10 million procedures, generates high quality endoscopic videos and system data, offering valuable resources for intelligent surgical vision systems. However, detecting and localizing surgical tools remain a challenge due to the time consuming process of manual annotation. And our project, SurgVU, tackles this by leveraging the deep learning techniques with Da Vinci's surgical videos. We initially explored a supervised grad cam CNN for tool detection, but for better localization, we trained a fully supervised YOLO detector using curated annotated frames and tailored data augmentation. For a method overview, we have three sections. The first one is dataset and preprocessing, the second one is the model development, third one is training. Our dataset provided by Mikai comes from 155 Da Vinci robotic-assisted surgeries, totaling over 840 hours of 720p and 60 fps video. Initially, the data included tool presence label without bounding boxes. To reduce redundancy, videos were downsampled to 2 fps and border masking was applied to focus on the surgical field. The dataset faced a class imbalance, with some tools such as needle drivers appearing frequently, while others such as clip appliers and staplers were underrepresented.
So for our development phase, we explored two different approaches. The first approach is to use a weakly supervised model, such as a ResNet 50, with a combination of a grad cam layer. So the ResNet 50 base model would help predict the tool's presence from our data, while the grad cam layer would provide visualization by extracting the key highlight features from our ResNet 50 model and generate a heat map, which can be used to create bounding boxes for our output. However, we found that this approach is not very suitable since it has an inconsistent heat map generation and also its inability to provide the precise localization. And given the time constraint that we have, we decided to shift to a second approach. So in our second approach, we use a YOLO V8 based model, and we found that it offers the best balance between performance and training efficiency given its small size. And for its architecture, we found that the YOLO V8 uses a CSP darknet for its backbone, and it is responsible for feature extraction, while a pan-FPN for the neck is responsible for multi-scale fusion. And the YOLO V8 model has an anchor-free detection, which helps reduce the complexity and enhance the precision for small or irregular tools detection, which is often seen throughout our data. And here's a little look at our model architecture for the YOLO V8S.
Our training used the best YOLO version 8 model. We generated pseudo labels on unlabeled surgical frames, keeping only predictions above 0.85 confidence threshold, and combined them with manually labeled data to expand the dataset. The final configuration trained the model for 58 blocks with early stopping and adaptive batch size, using around 60% of GPU memory and a learning rate of 5 times 10 to the power negative 4. We also apply data augmentations techniques such as horizontal flipping, geometric transformations, and mosaic augmentations. As for results, the best model achieved a mean average precision of 0.2087 using a YOLO version 8 small size. The model successfully detected common tools like needle drivers and monopolar curve scissors with high accuracy, but still struggle with rare instruments such as clip appliers and slippers. The main limitations include class imbalance, occlusion issues, and duplicate bounding boxes, which reduce precisions. However, these results provide a strong foundation for further improvement in the surgical tool detections.
In the future, we plan to address key challenges such as class imbalance, tool differentiation, and model robustness by implementing data balancing technique. Additionally, we'll enhance the model by increasing dataset diversity and also optimizing hyperparameters. So this will allow the surgical face recognition for a more comprehensive understanding of surgical workflows.
And this is the end of our presentations. Thank you for listening.